In this example, we're asked to compute the integral of secant squared pi x in two different ways. And the first one is to do it informally by guessing and adjusting the chain rule backwards. And what I mean by this is when I look at the integral, I see the secant squared function. And I know that secant squared comes from differentiating the tangent function. And of course, I have this complication that the argument is pi x instead of just an ordinary x. And so I'm going to guess that maybe the thing I differentiate to get that integrand is tangent pi x. Then I check my guess by looking at what happens if I actually differentiate this thing. And in practice, this part would be done sort of mentally as I'm guessing and adjusting. And I get the derivative of tangent pi x with respect to pi x, and that's secant squared pi x. And then the chain rule says, well, now you have to multiply it by the derivative of pi x with respect to x, and I get an extra factor of pi. So I've essentially got my answer to the indefinite integral, but I missed by a factor of pi. And so what I do if I go back to the original integral is I simply prepare the integrand for doing the chain rule backwards. I'm going to pull a factor of 1 over pi out of the integral, and I'm going to put a factor of pi into the integral. So constants are free to move in and out of the integral, and I'm taking advantage of that flexibility. And now the thing in my integral is exactly the derivative of tangent pi x, and so I end up with 1 over pi tangent pi x plus an arbitrary constant c. In part B, we're asked to do the same integral using a formal u-substitution. And really the point I'm trying to make here is that the vast majority of u-substitutions are really just trying to account for this simple sort of adjusting for what the chain rule does when you run it backwards. So I'm going to let u be equal to my inner function here, pi x. Well, that means du dx is pi. The reason I'm doing this is so I can transform my differential in addition to the rest of the integrand. And so I get du equals pi dx. Now, if you like, you could replace dx with du over pi. But my preference is to go ahead and just throw the pi into the integral using the flexibility of constants to move in and out of the integral. I replace pi x with u, and I'm going to throw a pi in next to the dx, and that'll give me du in the next step. And of course, you can't just throw pi's wherever you want. You have to compensate for it out in front. And so I get 1 over pi integral of secant squared u du. And that's a standard integral again. I recognize secant squared comes from the derivative of the tangent function. So I have 1 over pi tangent u plus c, and then I replace u with pi x, the original definition of u, and I'm done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.